Okay, Sturm-Liouville equations. So what we'll do here is we'll define them, and then we'll show a couple of properties that are useful for these things. So these are ordinary differential equations, so ODE, and the actual equation is p of x, y prime, the derivative of all of that, plus q of x, plus lambda r of x, times y equals 0. So that's the actual ODE. It's a second order ordinary differential equation. Domain x is our independent variable, so we want x to be between between two numbers a and b, and lambda, this thing here, is a real number to be determined later. Okay, so Sturm-Liouville equations have boundary conditions, so we'll list those. And so the boundary conditions are a little bit weird. So we have two numbers, C1 and C2, that are not both 0, and two numbers, D1 and D2, that are not both 0, so that if y is a solution to the ordinary differential equation, then we have C1, Y1, evaluated at A plus C2, there's no 1 on the y, it's just y. Y prime of A equals 0, and D1 y at B plus D2 y prime at B equals 0. So if we have any solution to this equation, it has to satisfy these equations. And the C1 and C2 are given at the beginning of the problem, right? Every solution has to have the same C1 and C2 for the problem. There are regularity conditions. Which are that P prime, Q, R are continuous on the entire interval, including the endpoints, and that P and R are both strictly greater than 0 on this interval. So a regular Sturm-Liouville equation is one that has all these conditions. A singular Sturm-Liouville condition either has infinite domain, and Schrodinger's equation from quantum mechanics has that, or violates at least one regularity condition. Usually that means that one of the functions P prime, Q, or R is not continuous at the endpoints, or that either P or R is 0 at the endpoints. Problems at the endpoints at either A or B are dealt with by dealing with limits, so you can handle singular Sturm-Liouville equations. And also, the number Lambert is called the eigenvalue. And why is that? Why is it called an eigenvalue? Well, the Sturm-Liouville equation, if you differentiate that first term, right? The first term is P y prime quantity y prime. So if you differentiate that, you have to use a product rule there, and you get P y double prime plus P prime y prime plus Q y equals minus lambda R y, right? So we differentiate that first term, remove the minus lambda R over to the RY over to the right. And then we'll divide through by R. And we have this equation. Remember that R is strictly greater than 0, so we can divide by it. So we'll call it T. We define it like this. And so what that means is then that the Sturm-Liouville equations can be rewritten as Ty equals minus lambda y. And T is a linear operator, right? It's basically works the same way matrices do. And so that means it's got eigenvalues and eigenvectors. And the eigenvector pair is any solution to an equation like this where T is a linear operator. And so lambda is in fact a eigenvalue, and then the y's, the solutions to the Sturm-Liouville equations, are in fact eigenfunctions that we're looking to find. So that's why it's called eigenvalues. So 3 things that we want to show. 3 important properties. Of solutions, well, we'll just make it of Sturm-Liouville equations. The first is, and this is for regular Sturm-Liouville equations. You can show the same thing for many singular Sturm-Liouville equations, but it gets a little more complicated. Eigenvalues are real and discrete. Which means these things. You can put them in a nice order. Lambda 1 is less than lambda 2, less than lambda 3. None of them are equal to each other, and there's a little gap between each of them. And the limit as n goes to infinity, lambda n marches off to positive infinity. The other thing is that if we have 2 functions that are eigenfunctions for the same eigenvalue, then they're linearly dependent. Right? One's a multiple of the other. Or another way to say this is the eigenspace of each eigenvalue is one-dimensional. This is important when we go to deal with expanding functions in terms of solutions to Sturm-Liouville equations. And the third thing, and the thing that we are most interested in is, and the thing, only one of these I'll actually prove, if lambda I does not equal lambda j, then yi, which is an eigenfunction for lambda I, and yj, which is the eigenfunction for lambda j, are orthogonal. Of course, orthogonality requires having a inner product, and the inner product is this. And that's from the Sturm-Liouville equation. If you look at the Sturm-Liouville equation, there's an R of x floating around. That has to be positive, and we can make the inner product be equal to that. So these first two things, I'm not going to prove. You would see them in perhaps in a more advanced ordinary differential equations class. But we will look at this third thing. Why is it that yi and yj are orthogonal for this particular thing? And then why is that so important? Why do we care about Sturm-Liouville equations anyway? So a quick reminder about matrices. So if we have a 2x2 matrix, we'll call it A11, A12, A21, A22 times x1, x2 equals 0. We'll call this matrix here M, traditional letters from a matrix. So this is a theorem we see in linear algebra. So this equation has a unique solution x1, x2 equals 0, 0, if and only if the determinant of M equals not equal to 0, or A11, A22 minus A12, A21 does not equal 0. Okay, so kind of an important thing there. And so if I set up a matrix equation like this, if I can demonstrate that it has multiple solutions, right, then that means that the determinant is 0, and this particular thing, which is the determinant, is equal to 0. So unique solution means the determinant is not equal to 0. Multiple solutions means that these things are equal to 0. And why is that important? Well, this is where the weird initial conditions come in. So suppose y1 and y2 are solutions to the same Sturm-Liouville equations. That should be an x. So what are the initial conditions, which are a little bit weird? Tell us about these things. Well, it tells us that C1 y1 of A plus C2 y2 of A equals 0, and C1 y2 of B plus, there should be a prime there, C2, that should be a y1, y2 prime of A both equal 0. Okay, and what we actually know is that not both C1 are 0. At least one of them is non-zero. So if we rewrite this as a matrix equation, we can rewrite it with y1a, y1 prime a, y2b. Oh, God, I don't know why I put a b there. It's supposed to be an a. y2a, y2 prime a times c1, c2 equals 0, 0. So what's that telling us? That's telling us that the matrix equation y1 of a, y1 prime of a, y2 of a, y2 prime of a, x1, x2 equals 0, 0 has multiple solutions. 0, 0 is always a solution, but so is C1, C2, because at least one of C1 and C2 is not 0. And so what that tells us is that the matrix, the determinant of this matrix is not 0 for y1a, y2 prime of a minus y1 prime of a, y2 of a equals 0. And the same argument holds with B instead of A on the right side of our interval, because D1 and D2, which are the constants for x equals B, also have to both be not 0. So we have these two results, and this is sort of what the initial conditions, the boundary conditions, are set up to tell us. And this will become important later. Okay, so what we want to show is the following, that if we want to show orthogonality, if yi, yj are eigenfunctions of lambda I, lambda j respectively, with lambda I not equal to lambda j, then the integral from a to b yi, yj r of x dx equals 0. Or in a different meaning, if you think about that integral as being an inner product, it's telling us that these two functions are orthogonal. Okay, so how do we actually check this? So solutions, eigenfunctions, that means there's solutions to the Sturm Liouville equation with eigenvalues lambda 1, lambda I, lambda j. So being solutions, what does that mean? Well, if you're a solution to a differential equation, that means if you get plugged into the differential equation, you work. So there should be a prime there. Q plus lambda I are yi equals 0, and p y sub j prime plus q plus lambda j r y sub j equals 0. So keep in mind that p, q, and r are functions of x, and x is between a and b, and y and yi and yj are also functions of x, but they're solutions to the equation. So what we'll do is we'll multiply first by top by y sub j, bottom by y sub I. So we get y sub j times p y I prime prime plus q plus lambda I r y I y j equals 0. And then we get y sub I times p y sub j prime prime plus q plus lambda j r y sub I y sub j equals 0. Now we'll subtract bottom from top. And what does that give us? Well, we get yj pyi prime prime minus yi pyj prime prime. And now we have to be a little bit careful here. We've got q yi yj, q yi yj. So when we subtract, the q terms are going to cancel out. But lambda I and lambda j are different. So we'll end up with plus lambda I minus lambda j, yi yj r equals 0. And now this, our goal is to show that we want the integral of this to be equal to 0. So what we're actually going to show is oh, don't know what happened there. If I can undo that. Okay. So what we want to do is to show that the integral of this equals 0. So to do that, we're going to have to transform that a little bit. So let's see, how many pages do I have left? I've got plenty of space left. So I'm just going to move my cursor down here so I don't accidentally bonk it. So what do we have then? We have lambda j minus lambda I, yi, yr, no, don't know why that's an r, that should be a j. Yi, oh, wait, I think the undo button actually does work. Okay, so yj times r equals yj pyi prime minus yi pyj prime. Those are both primes. And as I noted, this should be a j. So all I did here was I took this term, what we want to be equal to 0, and moved it to the other side of the equation. That just meant changing the sign on the lambda I minus lambda j to lambda j minus lambda I. And what we want to do is to deal with the right side a little bit. So what can I do with this? I can differentiate it all out, and it becomes yj p prime yi prime plus yj pyi double prime. So this is a product rule. You get derivative first times the second plus second times the derivative first. All of it's multiplied by the yj. And then we also get yi p prime yj prime minus yi p yj double prime. Excellent. So, and we'll just carry that left-hand side down. So what can we do with this? We can regroup everything by grouping it by p primes and p prime and p. So we'll look at the p prime terms, yj, yi prime. That's this one, and the other p prime term is that one, minus yi, yj prime. It's good practice sometimes to put little check marks over things when you're rearranging so that you don't lose track of them. Here's a term, p yj plus y times yi double prime minus yi yj double prime, which is this one. So I've got all four terms in there. And that's all equal to the left-hand side, which I'm not going to rewrite every time, but I'll put in dittos to remove that by. So this part, this is beginning to look like a product rule, right? I've got a derivative of something times something plus the function times something, right? There's a p prime and there's a p. So if the derivative of this is equal to that, this is exactly a product rule. So I'm going to modify this a little bit. We'll write down the p prime term. And then below it, write down what we have. So we've got yj times yi double prime. Now, if we differentiate this according to the product rule, we should also get a yj prime, yi prime. And then we have this minus yi, yj double prime. That's this term here. But if we differentiate this according to the product rule, we should get not only this term, but we should also have minus yi prime, yj prime close. And notice that now I'm actually justified in using that equal sign because these two terms that I added in they actually add to 0. So I haven't actually changed anything, right? I just added 0. That doesn't change anything. But I added 0 in the form of yj prime, yi prime minus yj prime, yi prime. And what that actually means now is that my left-hand side, derivative of the first times the second plus the first times the derivative of second is actually the derivative of p times yj yi prime minus yi yj prime. And if the question you're asking yourself is, how would ever someone think of that? The answer is, years of practice and playing with differential equations, right? If you learn enough about differential equations, you start recognizing these kinds of patterns and when you can actually add things in. Great, so now we're cooking because we can now integrate both sides. And let me write down what my left side was the whole time instead of having this thing. That was lambda j minus lambda I times yi yj r. So now we can integrate both sides. We get integral from a to b, lambda j minus lambda I yi yj r dx equals integral from a to b p d by dx of p yj yi prime minus yi yj prime close bracket dx. So lambda j minus lambda I, this is just a constant. So that comes out of my integral. Integral from a to b, yi yj r dx. And remember that the goal is to show that this integral equals 0. This integral is the integral from a to b of a derivative. Fundamental theory of calculus says that is just whatever the function is. So this is p yj yi prime minus yi yj prime evaluated from a to b. Great. So what do we have? We have lambda j minus lambda I integral from a to b yi yj r dx equals what? P of b times yj of b yi prime at b minus yi at b yj prime at b, parentheses, and this should be a prime there, minus p at a yj of a yi prime at a minus yi at a yj prime at a. But the things in the parentheses by the little matrix calculation we did above are both equal to 0. You can go and check that. Great. So what does that tell me? We know that this doesn't equal 0 because lambda j and lambda I are different eigenvalues. So we have this nice result, which we think of it in terms of inner products, is that the eigensolutions to Sturm Liouville equations are orthogonal for this particular integral, for this particular definition of inner product. So that's very nice. So why is this useful? So each eigenvalue, we didn't prove this, but it's true from above, has a one-dimensional eigenspace. So for each lambda I, you can pick a wi, a particular wi, a particular solution that corresponds to that eigenvalue. And we know then that we have picked up all the possible eigenvalues, all the possible eigenfunctions, because all the eigenfunctions for lambda I are multiples of yi. There are infinitely many such pairs. And finally, the eigenfunctions that we pick from these pairs are all mutually orthogonal. Great. So what does that mean? Well, the span of a set of vectors, so the span of the yi's that we've picked is all functions that are linear combinations of the eigenfunctions. So the span of that is just all linear combinations. Now, what's vector space we're living in? We're living in the set of functions. So span of this set is a subspace of the set of all functions defined on AB. So if we take a function that is in the span, so if f is something that's in the span of the eigenfunctions, then f equals a sum, I equals 1 to n, a sub I equals 1 to infinity, a sub I, y sub I. Now, the fact of orthogonality tells me that the inner product of f with any particular eigenfunction is, well, we know what f is equal to. It's this sum, I equals 1 to infinity, a sub I, y sub I, comma, y sub n. And we know that inner products are linear, so that means we can rewrite this as a sum, I equals 1 to infinity, a sub I, y sub I, comma, y sub n. And then we know that these things equal 0 unless I equals n, right? Any two that are different, their inner product is equal to 0. So this whole thing comes down to that. So the nice thing about eigenfunctions being orthogonal is that any function f that is in the span of the eigenfunctions can be represented as a series, and the coefficients of those series can be found by this formula. Oh, I forgot my R of x. There's an R of x in there. That comes from your Sturm Liouville equation. So, and we've seen this over and over again. Every time we solve a PDE, we get a set of orthogonal functions, and we find the coefficients by looking at the inner products. And why did that keep happening? Well, all the equations we ran into were Sturm Liouville equations, and so every time we did orthogonality, we were actually relying on the orthogonality of Sturm Liouville eigenfunctions. So note that there's this statement that we need f to be in the span of the eigenfunctions. The fourth property of these Sturm Liouville equations it's hard to determine exactly what the span is, but you can show, and we will not do so, that piecewise smooth functions are in the span of these eigenfunctions of regular Sturm Liouville equations. And piecewise smooth functions at this point are really the kinds of functions that we've been dealing with as boundary conditions and as even the statements of our PDEs. So basically, the Sturm Liouville theorem theory underlies a lot of what makes separation of variables works. You do the separation of variables, you get ordinary differential equations. Ordinary differential equations turn out to be Sturm Liouville equations, which means if we find the eigenfunctions for the solutions for the ordinary differential equations, two very nice things happen. One is that the eigenfunctions are orthogonal, so we can do this whole thing about finding the coefficients. And the second thing is that piecewise smooth functions can be represented as sums of eigenfunctions. And that works out very nicely for figuring out these solutions to these equations.